It's time to finish off the connection between integrals and areas once and for all. I mean, we've talked about it quite a bit. We have a tool now available, the Fundamental Theorem of Calculus, to effectively compute areas, at least for simple functions like polynomials and stuff for which we can find antiderivatives. So now let's just go through the whole thing one more time. Let's see the right pictures and then move on. So, well, one of the main motivations for the definite integral, of course, was the definition of areas. But when you're looking at the integral from -1 to 1 of x cubed, then what we know by the fundamental theorem of calculus is that that is 1/4 x to the 4th in the boundaries -1 and 1, which is 1/4 minus 1/4, which is 0. And that's, of course, counterintuitive because there is an area that is bounded by x cubed, and it's a non-zero area. Of course, we also know the solution to this riddle, and that is that if we're looking at x cubed, then x cubed bounds the area that is marked here in the picture, but this area is counted negative, this area is counted positive, and because of the symmetry of x cubed, which is an odd function, the negatively counted area here and the positively counted area here cancel each other out. Okay. So the thing now is that we somehow need to make sure that as we work out the area underneath a function, let's see if I can stop this right, that we distinguish between oriented area, which will just be the integral, and overall area. And basically, the problem with the oriented area is that when the function is below the x-axis, your rectangles have negative height, and so the symbolic way to handle it would just be to say that for the area we just integrate the absolute value of the function, but that is fraught with its own problems because, of course, the absolute value is rather hard to integrate symbolically, but the counting works out all right, right? I mean, here we've got negative area where this is already positive, and then we keep adding to the positive area, whereas the positive area that comes on the right here just cancels stuff back out. So what we need to do is we need to somehow be able to compute the integral of the absolute value or to find a substitute. And really, the absolute value is something that you do on a computer algebra system that doesn't care how to set things up symbolically for the symbolic computation. The methods in this presentation will be the ones to use, and it's just that we have to change things when the negative signs change. Okay, so the problem is that the definite integral counts areas below the x-axis negatively. We've heard that often enough now. The theorem is very simple, and that is that if you've got an integrable function, then if the function is greater or equal than 0 for all x in the interval a, b, then the area bounded by the function, the x-axis, and the vertical lines x equals a and x equals b is just the integral of the function from a to b. And if the function is less than or equal to 0 for all x in an interval ab, then the area bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is negative the integral of f of x dx from a to b. Okay, and that's of course the same picture that we've also seen before. Areas above the x-axis are counted positive, areas below the x-axis are counted negative. Okay, so how do we make sure that negative areas get that extra negative sign that makes them positive if we don't just stick the absolute value in there, which really for symbolic integration is not an option? Well, to compute the area between the function, the x-axis, and the vertical lines x equals a and x equals b, we can do the following. We draw a quick sketch. We figure out in which subintervals of the interval ab the function f is greater than 0, and in which intervals the function is smaller or equal than 0. And we compute the areas on those subintervals that we've just found up here. And then we add the areas, and that's it. So how does that go? Well, we want to find the area that is bounded by the vertical lines x equals 1, x equals 5, and the function f of x equals x squared minus 16, and the x-axis. Well, here's the picture, and here's the area. This area is counted negative, this area is counted positive, so we apparently have to cut the interval up, apparently at 4, and then do something different from 1 to 4 than what we do from 4 to 5. Okay, now just to make sure, the way you figure out where things switch, of course, is that you just set the function equal to 0 and solve. So x squared minus 16 equals 0 gives us x squared equals 16, gives us x equals plus minus 4. And then similar to optimization, where we had to make sure that we only look at the solutions that actually are in the interval, we realized that only x equals 4 is in the interval from 1 to 5, and so that's the only one we need to deal with. And so now the area is negative the integral of x squared minus 16 from 1 to 4, plus the interval from 4 to 5 of x squared minus 16. And that's because from 1 to 4 the function is below the x-axis, and from 4 to 5 it's above the x-axis. The computation itself then is very simple, and you can do several things. You can compute those integrals separately, or you can compute them in parallel. That I leave to you, just depends on what works better for you. Well, here what do we have? We have the antiderivative, which is 1/3 x cubed minus 16x. For the first interval, we take the antiderivative from 1 to 4. For the second interval, we take it from 4 to 5. And now we just have to plug in numbers. Well, let's see. 4 cubed is 64, so we get 64 thirds. Minus 16 times 4, it's 64. Minus, now again, bookkeeping. Make sure you keep your parentheses around the stuff that you subtract. 1/3 minus 1 is 1/3. 16 minus 16 times 1 is minus 16. Close the parentheses. First term taken care of. Keep the big parentheses. 5 cubed is 125, so we get 125 over 3. 5 times 16 is 80, so minus 80. Minus, keep the parentheses, so you're subtracting off the stuff on the lower bound. Well, 4 cubed is 64. 64 over 3 minus 4 times 16, which is 64. And you know what? Rather than playing mental arithmetic and all that, we know how to compute that, and it turns out to be, well, okay, so I did some combinations here. Let's see, 64 minus 1/3 is 64 thirds minus 1/3 is 64 thirds. 64 minus 16 is 48, and then, well, we had negative 48 with this negative sign gives us plus 48, and the minus sign here gives us the minus sign there. And 125 over 3 minus 64 over 3, yeah, that's 61 over 3. And 64 minus 80 is negative 16, yes. And then we get, what, 32 minus 2/3, and that's 31 plus 1/3. Note that I typically don't use a mixed fraction, because those things get confusing with multiplication of fractions. The answer is 31 plus 1/3. And well, now we can also look at that. Basically, the big thing is we've got to mind the zeros. And here's what happens. Well, the area underneath the axis, the integral would count as negative, but the absolute value, and really what we're doing is the absolute value is negative f of x around here, and it's positive f over of x around here. So that's what the split does. The algorithm, as well as when we're integrating the absolute value, just gives us the positive area, and we get the 31.33333 and so on. That is the 31 plus 1/3 that we also computed. And well, that's it already for that one, right? That's the whole thing. And so we move on. Next example, we want to find the area that is bounded by f of x equals 14 minus 5x minus x squared and the x-axis. And of course, the first thing that you might say there is, we don't have a left and right bound, but that just means that somehow there have to be enough zeros to trap an area, and that's exactly what happens, even though we're going to try this without pictures first. Namely, we take our function, set it equal to 0. Well, okay, that's a quadratic. Let's write that in the way that we're more used to seeing. Negative x squared minus 5x plus 14 equals 0. Find the zeros, quadratic formula, negative negative 5 plus minus square root 5 squared, 25. Minus 4ac, so minus minus is plus, and 4 times 14 is 56, divided by 2a, which is negative 2. 25 plus 56 is 81, and the square root of that is 9, so this is 5 plus minus 9 divided by root 2. Let's see what is divided by minus 2. And let's see, that is 14 divided by minus 2, so negative 7, and negative 4 divided by minus 2, negative 7 and 2. Right. Okay, so that means that the area is the integral from negative 7 to 2 of negative x squared minus 5x plus 14, or the negative of that. And, well, what do we know? We know that this is a quadratic with negative leading coefficient, which means it's a quadratic that's opening downwards. And so if you picture that, that's got to capture a positive area between its two zeros. Here's where you really want to have a mental image. We'll have an animation at the end. Okay, and now, well, now the rest is again quick computation because we find the antiderivative, negative 1/3 x cubed minus 5/2 x squared plus 14x from negative 7 to 2. Well, okay, so 2 cubed is 8, so we get negative 8/3. 2 squared divided by 2 is 2, times 5 is 10, so negative 10. 2 times 14 is 28. Again, minus. Make sure the bookkeeping works out. Big parentheses around the rest. 7 cubed is 7 times 49, which is 343. And then we have 3 negative signs and another negative sign, so 4 negative signs, so it's got to be plus, and so it's 343 divided by 3. Then we have 7 squared is 49, and 49 times 5 is 245. Divided by 2, that x squared should not be there. The minus sign is all right. Okay, now the x squared is gone, and we have negative 7 times 14, so that's 70 plus 28, that's 98, and with a negative sign it's minus 98. So that does work out, and then, well, then we just start adding things up, and let's see, what do we have? We have minus 98 plus 28, so that would be 126, and minus 10 is 116, so that's right. Then we've got all those thirds. Well, we've got negative 343 minus 8, so that's negative 351 thirds, and the minus 245 over 2, that still stays here, and so the answer will be in 6. Great. Well, maybe there's, oh yeah, sure, because 351 is divisible by 3. All right, so 351 divided by 3 is 117. 116 minus 117 is negative 1, so negative 1 plus 245 over 4 is 243, or 245 over 2 is 243 over 2. And basically, pictorially speaking, well, I guess I am not afraid to use my own content here. Pictorially speaking, the area is just the area underneath the function between the zeros, and it's 121.5, which is 243 halves, just like we said on the previous slide. So that finishes that one. The interesting thing now is, and this is something that we haven't tackled with Riemann sums and with direct setups, and that's because the computations would just get too epic, is that we can also compute the area between curves. So the area between x and x squared, for example, what would that be? Well, it's right there, right? Well, the integral, however, can only give us the area underneath the curve. And so the integral can give us this area underneath the straight line. It can give us this area underneath the quadratic. But what we can see is that the area between the two is exactly the area underneath the higher function minus the area underneath the lower function. And that's exactly how we're going to set up integrals of areas between curves. When f and g are integrable functions, and f is greater or equal than g in the interval ab, then the area between the function, between the graphs and the vertical lines x equals a and x equals b is the integral from a to b, f of x minus g of x dx. And if f of x is less than or equal than g of x for all x in the interval bc, I just for some reason wanted that interval to have a different name, then the area between the graphs and x equals b and x equals c, those vertical lines, is the integral from b to c, g of x minus f of x. So we always subtract the lower function from the higher function and integrate. And so the algorithm says exactly that. When we want to compute the area between the graphs of two functions in the vertical lines x equals a and x equals b, here's what we do. We get a quick sketch of f and g. We figure out in which intervals the function f is above the function g and in which intervals the situation is reversed. We compute the areas in these intervals obtained in step 2, and we're going to do that just like we did in the theorem just shown, and then we add up the areas, and we're done. So, as an example, let's just go ahead and find the area between the graphs of f of x equals x squared, g of x equals x, x equals minus 2, and x equals 2. And, well, that splits up into 3 parts, right? Here's the first part. Here's where f is greater than g. Here's the second part, that's where g is greater than f, and here's the third part, which is where f is greater than g again. Alright, so in order to find those, well, of course it's a quick computation, but let's work it out. X squared, you just set the two functions equal. Here it's tempting to cancel the x, but if you do that, you have to mentally remember x equals 0 is a possible solution. It's certainly safer to just bring everything to one side, then factor out the x, and then realize that that has two solutions, namely x equals 0 and x equals 1. As this becomes more complicated, of course, you use the quadratic formula and things like that, and then it's always the same principle. Set the functions equal, and then just solve the equation. Okay, so our area is the integral from -2 to 0 x squared minus x dx, and that is because x squared is greater than x there, minus the integral from 0 to 1 x squared minus x dx, so I put a negative sign in there and didn't reverse that, plus the integral from 1 to 2 x squared minus x dx. And now we work that out. Well, the antiderivative is x squared of x squared minus x is 1/3 x squared minus 1/2 x squared, and it's that all the way through. And then we have the bounds in there, and so now we just work that out. Well, at the upper bound, this function is equal to 0, again, minus big parentheses, -8/3 minus 2. Then we have at the upper bound here, we've got 1/3 minus 1/2, because we're plugging in 1, minus at the lower bound, all this stuff is 0, and we just kept the minus sign outside here. Plus, and here at 2, well, at 2 we get 8/3 minus 2 minus, again, big parentheses, and the value at 1 is 1/3 minus 1/2. And as we work that out, I think that's still something, that's just the 3 parentheses worked out. So let's see. 2 is 6/3, so we get -14/3, which is 14/3. 1/3 minus 1/2 is -1/6, and another negative sign gives us a plus 1/6. And then we have 8/3 minus 6/3 would be 2/3, minus 1/3 is 1/3. And then we have 1/3 minus negative minus -1/2, and 1/2 is 3/6, right? So we get plus 3/6, 3/6 plus 1/3, so it's 3/6 plus 2/6, which is 5/6, which is exactly what we wanted to have here. That's 14/3 plus 1, so that should be 17/3. And that's that computation. So again, as soon as you've got the setup, the rest is routine computation and stuff that just helps us practice with numbers somewhat. All right, I've got another one here. Okay. Right, sometimes you just integrate along a different axis, and that really shouldn't be too bad for us either. So for example, when we want to find the area between the graphs of y equals the third root of x, the y-axis, and y equals -2 and y equals 2, well, here's the third root of x, that's just fine, but this time we're interested in the area between the graph and the y-axis. Okay, now you can just tilt your head sideways and realize that all we have to do is integrate along the y-axis, so we would need a dy integral, and everything will work exactly the same way. So let's go ahead and do that. The area will be the integral of the function dy, and if y is third root of x, well then x is y cubed, right? And if we're going along the y-axis, then we're integrating x equals y cubed. So we're integrating y cubed from -2 to 2 and from 0 to 2. And it's below the y-axis from -2 to 0, so that means that we have a negative sign here. Okay, well, we integrate that. The antiderivative of y cubed is 1/4 y to the 4th. We keep the negative sign. We've got the bounds in both cases. And now plugging in ought to be pretty simple. Yes, it is, because at the upper bound it's 0. At the lower bound we get 16 divided by 4, which is 4, so 0 minus 4. Same thing here. At the upper bound it's 16. At the lower bound it's 0. Minus 4 plus 4 gives us 8. And that's the answer to that problem. All right, we're going to close out with the computation of the area of an ellipse. Now, I may have done it in one of the earlier presentations, or it may be in the book, that we can certainly use integration formulas in order to verify the area formula for a circle. But that's in some ways a little bit boring because we've known the area for a circle for a long time. Now for an ellipse, well, for an ellipse we don't quite know the area. I mean, we know what an ellipse is, right? It's a circle with two radii. It's sort of a circle that got bumped on the head or so and then shrunk in one direction. Well, let's see if we can work that out symbolically. So if we were to compute the area of the ellipse, x squared over a squared plus y squared over b squared equals 1. What do we have? The area would be twice, because the ellipse, and here's where I didn't put a picture in, and I'm not sure if that was intentional or not, but basically draw yourself an ellipse. And what you've got is the ellipse has equal parts above the axis and below the axis, which means the integral of the function will have to be doubled to also capture the stuff below the axis. So we get 2 times the integral from negative a to a, and we're integrating along dx. So what are we doing here? We're solving for y. Well, y squared is equal to b squared times 1 minus x squared over a squared. So y squared is b squared times 1 minus x squared over a squared, and if we take the square root of that, of course, the square root of b squared is b, and the 1 minus x squared minus a squared stays underneath the square root. Okay, so that is a symbolic integral, and well, that symbolic integral is reasonably challenging, of course, but let's see what we can do with it. If we do a u substitution with transformation of the boundaries, we say u equals x over a, then du dx is 1 over a, which means that dx is a times du, of course. And so that means our integral is 2 times, and now we transform the boundary. When x is negative a, well, u is equal to negative 1. When x is equal to a, u is equal to 1. We keep the b. The integral goes over the square root of 1 minus u squared, and then we have the a du at the end. And so that's 2ab integral from negative 1 to 1 square root of 1 minus u squared du. And the antiderivative of square root 1 minus u squared du can be computed. You just have to work out the antiderivative there with an integration by parts. It's an integration by parts trick where you just say this is 1 times the square root here, and then you do integration by parts where you integrate the 1 and differentiate the square root. And yeah, that's computationally rather hard, but if we look at this geometrically, let's remember that the main idea for this presentation was interpreting integrals as areas and using integrals to compute areas. Well, that cuts both ways. The function square root 1 minus u squared, that's a semicircle of radius 1. And we're integrating over the whole semicircle of radius 1. Well, what's the area of a semicircle of radius 1? It's pi r squared. It's pi times 1 squared. It's pi, and then you take half of that, of course, because it's a semicircle. So this ends up being 2ab times pi halves, and that's pi times ab, and that in some ways actually is a rather beautiful and a natural formula, because what else should the area of an ellipse be, right? When you've got a circle, then a is equal to b is equal to r. You've got the same radius, and the area is pi r squared. Well, it makes sense that the area of an ellipse ought to be pi times a times b, pi times the radius in the x direction times the radius in the y direction. Of course, reasoning by analogy doesn't give you the answer there. This is more like a tool that can help you to remember what the area of the ellipse is, but it is a result that certainly makes a good bit of sense. All right, so you've seen what to do. Basically, you visualize either mentally, as I wanted you to do that here, and if that didn't work mentally, just find an equation, find the picture of the ellipse in a book and work it out with that. Make sure you understand what we're doing here, and then just work some examples. As soon as you've got the setup and the visualizations, the computations shouldn't be that bad, or if the computations get ugly, it's most likely to make you practice integration techniques, which is not a bad thing to do either. All right, I'll see you for the Fundamental Theorem of Calculus in its derivative form, which is a really short presentation that finishes our block on talking about the Fundamental Theorem of Calculus. Bye.